Thank you very much. So thank you all for being here. I'm Sébastien Crozet. I've been working on open source for Rust for quite a while now. I've been working on linear algebra, physics simulation, geometry. And today I'm very, very excited to present this new project I started a few months ago, which is about GPU computing, especially for scientific computing. So it's named WGMath. So WGMath is like the idea of the project, but the actual Rust libraries have different names. We will see a bit later. So what problem are we trying to solve with WGMath? Today, scientific computing is very, very hard. Like even just linear algebra, which you will end up doing if you want to make any kind of scientific computing program, is very difficult. So you don't want, when you start your project, you don't want to start from scratch. You want to benefit from the community, from the existing open source code, and you really don't want to write everything yourself, otherwise you wouldn't have time to focus on what makes your solution unique. So it's very difficult. You want the community. And the problem today is that the field of scientific computing is very, very much dominated by CUDA. So I guess everybody knows about CUDA. It's made by NVIDIA. It's a very fantastic system. It's very efficient. It has extremely great libraries, like you have QBLAS for linear algebra, built by NVIDIA itself, so it's extremely fast, very user-friendly. So it's a great standard, but it is a closed solution. You are tied to NVIDIA graphics cards. You are tied to the CUDA API. So it's not so great from a community perspective. And it's very unfortunate because even research papers right now, if they do anything with GPU computing, they will do that with CUDA. This includes machine learning, but also physics simulation, which is kind of my main field. So what can we do to open this to every platform? Now, obviously, I'm not the only one to try to run code into every platform. And here I can see a few alternatives. So in the first line, it's more like AI-specific solutions with Candle, GGML, Onyx. They all provide you with a bunch of tools so you can build your models and run them in any platform. So they all have a CPU backend, but they also have some some GPU backends, which are either based on CUDA, sometimes also Vulkan. I think Onyx also has a WebGPU backend, but it is specific to machine learning, so it doesn't really fit on what we want to do this, which is really scientific computing on the GPU for every community. Of course, we have OpenCL, which again has its own shading language, like a OpenCL C or OpenCL C++. It's very versatile, but today, at least from my point of view, it does feel like it's being a bit slowed down. Apple dropped support for OpenCL some time ago. I haven't seen a very good support of OpenCL on the web. I know there has been some effort, but I haven't seen this being adopted as efficiently as WebGPU, for example. And of course, we have Vulkan, which does not have web support and also doesn't have first-class support from Apple. There are a few other solutions as well, and these ones, at least these two on the right, are specific to Rust. It's two Rust projects. They let you write your GPU shaders directly in the Rust programming language. The first one, Rust CUDA, is specific to CUDA, so you write in Rust and then you can generate PTX files. And Rust GPU is specific to Vulkan. So obviously, they share the same kind of benefits and limitations of CUDA and Vulkan, but also there are specific to, they need you to use a specific version of the Rust compiler. Like you really have to use that version because it relies on a lot of complex compiler magic, which in practice makes it very difficult to use. Like I've been making a physics simulation framework with Rust CUDA. It works very well. You can use any NoSTD library if you want. But since the Rust language is evolving so fast, then what happens is your dependencies or even dependencies of your dependencies will start using the latest compiler versions. And so you are kind of stuck with like an old version of your dependencies because you cannot switch to this new compiler whenever you want. And updating ResCUDA, for example, to the latest version, I know it's a very, very difficult task. Hopefully this will evolve in the future. Like maintenance has slowed down quite a bit, but recently there has been some effort to merge these into the same organization and hopefully have something more up to date soon. And WESL is one project I'm very, very excited to see. It's kind of an attempt to standardize some extra feature for WGSL, like the shading language for WebGPU. So it lets you have some additional features like importing modules from another module, and also a lot of other compatibility, some more user-friendly abstractions like generics and etc. Like the standard is not like closed right now. It's very, very early stages, but hopefully this will give us eventually some very, very good solutions for reusing code across shaders and also some very, very nice tooling. And I'm hoping to use that in WGMath eventually. So the solution we've been using for WGMath is WebGPU, and in particular, because I'm writing in Rust, I'm using the WGPU implementation. It does support a lot of different backends, so it will support all the main platforms, including browsers, assuming that your browser does have an explicit support to WebGPU, which is not the case for every browser right now, but it's evolving quite fast. So with that in hand, what you do as a user of WebGPU is that you will, like as a developer, you will write your WGSL code once, and then it will automatically be translated into whatever system you are targeting. So it's very, very nice because you really just have to implement and optimize your code once. So what's WGMath about? So it's this idea of starting a community for scientific computing in every platform. So to start with this idea, I've built a few libraries here. So with WG Core, which is kind of more the lower level piece, which gives you some abstractions over the raw WGPU resources. And then we have more mathematical libraries. So I mentioned WESL, which is an effort to make shaders reusable, like having imports between shaders and hover toolings. Right now, it's not very ready yet, so I'm using something else which is named Naga Oil, which is maintained by the Bevy community. So with Naga Oil, it's a WGSL shader preprocessor. So you give it like all your WGSL files, and then it will parse some special statements that's specific to Naga Oil, and then it will let you import modules from different modules, have some kind of macro systems, etc. So what WG Core does is that it will define a procedural macro that we will see a bit later that really eliminates a large part of the boilerplate needed by Naga Oil. And it will give you a bunch of metrics, vector, tensor, structs, which makes very easy to initialize your matrices from an algebra matrices, for example. So an algebra is a linear algebra library in Rust. And it really tries to be as transparent as possible. Like it doesn't try to hide everything from you. It doesn't try to feel very like a black box. I try to make this transparent because if you want to do GPU compute into your project and you want to interface this with a game engine, for example, it's very, very likely that, for example, the device and the GPU device and the GPU queue have already been opened by your game engine and is completely owned by the game engine. So at this point, we really want to reuse whatever resources have already been created otherwise, and then we don't have to recreate the device ourselves, which can create some complication if you want to start having your compute buffers interact with whatever you use for rendering. So it really tries to make some utilities, but you don't have to use them if you don't need to. So that's WG core, and then we have a bunch of mathematical libraries. So you will see the names are kind of lazy. It's WG followed by some other project of mine. So WGBra is kind of an algebra, but as a WGPU version. WGParry is Parry, which is a collision detection and geometric library. But the aim of WGParry is to be that, but on the GPU. Same with WGRapier. So Rapier is a graphics engine, and WGRapier would be a WGPU slash WGSL version of Rapier. We also have WGML, which is inspired by GGML, which is like one of the biggest framework for building LLMs right now. And WGSparkle, which is inspired by the Sparkle library, which is a physics simulation library I've written in CUDA, and I've rewritten this in WGSL. So right now, all of this is very early days. So I've mentioned a few features in here, and I haven't implemented all of these features yet. Right now, the libraries which have the more features would be WGSparkle, and we will see a demo later. WGCore for building and sharing your kernels, and WGML for building large language models. So let's see what WGCore does for you. So here on the left, you can see that we have two WGSL shaders, and on the right we have a Rust file. So in our shader, we have two different files. We have composable, which would be like a piece of WGSL code you would want to reuse from a different shader, and it just defines two elements, like a structure and a function. And here, this is just regular WGSL code, except for this first line, the define import path line. So this line is specific to Naga Oil, and this is saying, okay, you can take this file, and with this path, which is a composable module, we can reuse symbol from this shader. So if we look at kernel.wgsl, it's again very standard WGSL code, except for this very first line, which is an import statement, which is telling, okay, I have somewhere in my code base, I have this module name composable module, and I want to import that as a dependency. And here I just name the module dependency. And then I can reuse some of these symbols. So you can see I have dependency, mystruct, and dependency shared function, which are both used in this file, but defined in a different file. Now, this is just like what you can already do with WGSL and Naga Oil. And where WG Core is doing something is on the Rust side. So if you were to use Naga Oil directly, you would have a bunch of boilerplate. But here with a block macro, you can make this very, very simple. So we have first this structure, which I named WG composable. You just have to specify that you derive the shader trait, and then specify the path to your WGSL source code. With just that, it will create all the boilerplate you need to make your shader reusable from a different piece of shader. And then we have a second part with WG kernel, which is very similar to the first one, but you have this extra line which is derived WG composable. And this line is saying, okay, my shader has a dependency to WG composable. So because WG composable is just a regular REST struct implementing the shader trait, which is like trait are a very basic REST feature, you can reuse your shader from WG composable very easily, even if WG composable was in a different crate. Like if it was a dependency on cargo, you could reuse your WG composable shader very easily that way. Yeah, one additional feature is that you see that WG kernel has this compute pipeline field. So if it has this field, the shader procedural macro will automatically see that it has this field and will generate all the boilerplate you need to instantiate this compute pipeline. So if we have a look into more details on what this shader trait is about. So on the left, you have what you write, and on the right, you have what you get automatically from the procedural macro. And in particular, it's interesting that you will have this part with the compose function. This is telling NagaOil, okay, I have this source file, and I want to make this available to other WGSL source file. So this is automatically generated. We also have a few extra functions which are not very useful for this case, like the from device. It's basically a no operation, and this is because we don't have any compute pipeline in this shader. And if we look at the second one, you will see that it's quite similar, but from device is not empty this time. We do have some actual code because this is where it will load load your compute pipeline for you. And you will see also in the compose function that it will call the composer from WG composable, which means that it will automatically make available WG composable into your kernel. So it's really about lowering the amount of boilerplate you need to write. But if you have something more difficult, like for example, you have a structure like WG kernel, but you need some additional field in that struct to know which compute pipeline you want to instantiate or something, then you cannot use the procedural macro right now, but you can still implement the shader trait yourself. So it's really just about making your life easier, but it doesn't prevent you from doing things your way if you need it. So here, it's just to show a little bit of how we can use that library, in this case, to write the Llama2 transformer. It's just to show that it looks quite nice. Compared to what we've seen before, this is hiding a few elements. Like you can see the queue function. It's something we have to implement ourselves. So this is what will queue all the kernel invocation for your compute pipeline. And here, everything like RMS norm, matmul, which is matrix multiplication, ROP, etc. All of these are structures very, very similar to this WG kernel thing. And they also have dependencies, which are all resolved with WG core. So in terms of demos, I have, for this conference, which is kind of the first time I release this project, so they got open sourced yesterday, I had two goals to show that it's really about addressing a wide range of scientific computing fields. So I have a physics simulation and a large language model. The focus right now was to focus on features more than performances. So it's not like state-of-the-art performances, but it does show that it works pretty well. So for the first one here, Okay. Yeah. So the first one is very simple. It's just running the Llama2 transformer. So if I press run, so here it will read a GGUF file which was derived from the dataset you can find in the llama2.c repository. So like it's a dataset with which was trained from a bunch of very small stories. So if you prompt this transformer with like an empty prompt, you will get a randomly generated story. So this is WGML. It has a loader for GGWeb files. It has a very limited support for quantization right now. Like it will just dequantize your information, but it will not try to run your math in their quantized form on the GPU at all. So this is something that needs to be improved in the future. So there is also a GPT-2 implementation, but the goal is to expose to you all these kernels so you can start building your own transformers if you want to. And for the physics simulation demo, so this is the front page of the project right now. I haven't a very comprehensive documentation, but one very interesting thing is that you can have some documentation of your WGSL shaders here. So it's using a third-party tool which is called Shader Docs. It reads your WGSL files and it will generate documentation from that. It's a documentation that looks very similar to RESTdoc, but it is more limited. So you can see that in the WGBra right now, we have like quaternions, singular value decomposition for 2x2 and 3x3 matrices, and similarities. So it's very far from the complete feature set of an algebra, but the goal is to get there eventually. So if I click here, you can see we have a bunch of documentation. So it's usable. It's not as good as RESTdoc, but you can really navigate your code. So it's a very good start. I'm hoping that eventually WESL will develop some better tooling, especially for documentation, but we will see. So if you were to go into this page, which is wgmath.rs, you have a couple of demos here, 2D and 3D, which is for physics. So to run this demo, you have to have a compatible browser, so compatible with WebGPU. It's not the case for every browser, and some browsers have only partial support. Like this won't run on Firefox, for example. And depending on your platform, like on your OS, it might work on some browsers and not others. So right now here, my browser is Arc, but basically it's like Chrome. It works also on mobile, like on my Samsung here with the Samsung Internet application. It works very slowly, but it works. And on my iPad, it also works. So it's really truly cross-platform. So if you open these demos, be aware that it will take a while to show up because it has to download like 20 megabytes of WebAssembly file because it's made with Bevy, and I haven't found a way right now to make this WebAssembly file smaller. So I have these preloaded here. So this is an NPM implementation. So NPM, material point method, is like a physics system to simulate a very wide range of different materials. And in this case, we have a huge cube of particles. If I zoom here, you can see we have a bunch of particles. So in totals, we have about half a million particles here. And everything here is just a bunch of sand. So if I play run, and again, I'm in the browsers, you can see that everything falls due to gravity. it does have some interaction with some invisible cubes in here. And this is using a lot of shaders. Like this is using a lot of shaders from the WG Sparkle crate, but also from WGBra, WG Parry, WG Rapier. So it's really experiencing the reusability of shaders across different crates. So right now I've wrote all these crates, but you can imagine that someone else wanting to create their own simulation, they could just start grabbing things from crates.io and building their own system. So yeah, this is just a bunch of sand. You can see that for 500,000 particles, it's running quite fast. It's slightly slower than real time. But at the same time, one very interesting thing I noticed, and I have to say, I don't know why, the web version is about 40% slower than the native version. Like running natively on your computer will be faster. I'm not sure why, because it's the exact same shader, but maybe Jim will know. I have a second demo here. So again, it's also NPM, and this time it's to simulate a purely elastic material, which will break down when it experiences too much forces, too much deformations. And the coloring here is based on velocity. Yeah, you can see it's also quite fast for 500,000 particles. And I have similar simulations based on CUDA, and yeah, turns out this WGPU implementation was about 3 times faster than the CUDA implementation, which does not mean that WGPU is faster than CUDA. It just means that my CUDA implementation was not perfect, but at the same time also that we can achieve very, very good performances with WGPU. So that was 2D. There is also a 3D demo, which this one is much simpler. It's just also a big chunk of sand. And yeah, we can see that it will fall and it will make a pile of sand. Interestingly, again, this is on the web, and the native version this time is not 40% faster, it's 3 times faster. Sorry, it's the other way around. Like the web version is 3 times slower than the native version. So I'm hoping eventually that maybe I can optimize something to get them at the same level. But again, it's still very, very nice performances, and this is running 2 times faster than my CUDA implementation of Sparkle. Okay, so let me just pause this. So in terms of roadmap, like I said, I started this project a few months ago. So it's very, very early days. Everything got open sourced yesterday. So for GOSIM, for this conference, the goal was to have an initial release to focus on the core architecture, so the WG core crate, to make a bunch of low-level operators, like for WGML and for physics and geometry, and to make these demos to really show that it can cover a wide range of very different scientific applications, and really promote the fact that the goal is to combine work from multiple communities so we can share shaders, and we can eventually reach a point where WebGPU becomes competitive compared to CUDA in terms of tooling and availability of libraries. So the goal for Q2 2025 and like the rest of 2024 is to grow the community. So I would be very, very happy to have some contributions, especially on the linear algebra side, because I know that writing a very efficient matrix multiplication algorithm is extremely difficult, and that alone could take weeks, if not months. Hot reloading, I do believe that the procedural macro from WG Core could give you all the boilerplate for a hot reloading automatically. That would be extremely cool. Like you have your dependency, and then if you modify something, it will detect that everything that depends on this has to be recompiled and propagate the changes automatically. So that would be very, very nice. and reaching feature parity with no STD CPU libraries. What I mean by that is that Rust has this concept of no STD libraries, which means that the library does not depend on the standard library. So an algebra, for example, can be compiled in no STD mode, and then you will have access to a subset of its feature, and that subset of feature is what I would like to implement here. So this includes all like transformation structure, like isometry, similarities. I already have similarities. Projections, etc., and also a bunch of matrix decomposition on small matrices, etc. And this also includes parry, which also has a no STD mode, and that would be all the geometric operations you might want to run on primitive shapes like cubes, spheres, cylinders, etc. And then for the second half of 2025, the goal would be feature parity with the STD CPU libraries. Again, by libraries, I mean Parry and Algebra, Rapier, hopefully GGML as well. And this one would be more focused on the kernel side, like writing actual algorithms that involve kernel invocations. So that would be, for example, having an actually fully functional GPU physics engine like Rapier. So having broad phase, narrow phase, force computation, etc. That would also include having more operations available for building large LLMs transformers. That would include like more advanced collision detection with triangle meshes, etc. And of course, general optimization, because we want this to run as fast as we can. Now, of course, I know this is probably a bit overly optimistic, but that's the ongoing goal, to reach as many features as we can, so we can really close the gap with CUDA in terms of scientific computing. And yeah, on top here you have like the repository link. Okay, so thank you very much for being here again, and yeah, it's very exciting to hopefully have this community for scientific computing reaching any platform.